again, should be pretty straightforward. I mean, most of this, it just comes down to like using your calculator, right? Probably would be a good idea of things to put on your half sheet, just like the instructions on what to do with your calculator. But, you know, it's your half sheet. You put on there what you want. Okay. And you guys saw, I hope that the homework quiz that was supposed to be Friday is now going to be today. All right. We're going to do it right now. Chapter 13 stuff. So we're going to talk a little bit about section 13.1 today. So when we talk about, or we're going to be talking again in this chapter more about polynomials. We talked a little bit last chapter about like what it means for something to be a polynomial. Here we're going to do some more work with polynomials. A lot of the things that we'll be doing though in this chapter are going to be revisiting ideas that we developed in Algebra 2. So there's going to be a good chunk of this material you'll see here in this chapter that'll be things that you hopefully remember from Algebra 2. There'll be some places where we do a little bit of extension, but a lot of this is going to be things that if you did a good job last year should be really familiar to you. And if they were things that you struggled with last year, hopefully it's an opportunity to get a little bit better at it again this year. Okay, so we're starting off talking about graphs of polynomial, and when we talk about the graph of a polynomial, typically we're interested in like two key features. So the first key feature we're going to talk about are extrema. And there's basically what we mean by an extrema is like the high or low points on the graph. So these high points we refer to as maxima, or that's the plural for the word maximum. And the low points we call minima. Again, that's the plural for the word minimum. And there's really like two kinds of maxima and two kinds of minima. So there's like four total type of extrema. So let's just kind of look at an example here. So let's say we have this graph here. So I see a maxima or a maximum here and a maximum here. Everybody agree with that? And then I see a minimum over here. Now, if I look at these two maxima that I've highlighted on this graph, these are actually two different types of maxima. So the one on the left is actually the highest point in the entire graph. So this one we'll refer to as a global maximum. So it's like the highest overall point. And this other one we'll call a local maximum, because it's just in its little neighborhood, it's the highest point, but there's other spots that are higher. Let's look at this minimum that we have here. Is this minimum local or global? This is local, right? Why is it local? and not global. It's the only minimum. Why is it not global? Because, excellent, because the arrow's at the end of the graph pointing down. There's lots of points lower than that one. Why don't the arrows at the end of the graph count as minima? Because any point you pick on that, because there's an arrow pointing down, there's another point lower than it, because those arrows go on forever. So those don't count as maximums or minimums, the arrows at the end of our graph. Does everybody feel okay with that vocabulary? Again, this is something we talked about last year in your Algebra 2 class, so it should be relatively familiar sounding, this terminology. And again, we're not going to do much past like looking at a picture and labeling points on a graph or something, so it's not, it's not super technical. We should take a moment though, and let's do this first. The other type of key feature are the intercepts. So the intercepts are points where the graph crosses the x or y axes. And axis there is just the plural spelling for axis. You probably don't see that very often, so I didn't misspell the word axis there. Okay, so let's think about this for a moment. If we're talking about the graph of a polynomial, how many y-intercepts can the graph of a polynomial have? Has to have exactly one, right? Can't have more than one because it would fail to be a function, because that would be, a vertical line, the y-axis. If it crosses that twice, that's failing a vertical line test. And because a polynomial has to go on forever in both directions, it has to cross it eventually somewhere, right? So one time exactly. How about x-intercepts? How many x-intercepts can the graph of a polynomial have? Really any number, right? So it could be 0, right? Could not cross at all. Imagine a parabola that just is above the x-axis, doesn't have to cross at all, but it could cross 1 time, 2 times, 3 times, 4 times, 5 times, however many you want. It's got to be a finite number. It can't cross infinitely many times. But as big of a number as you want to pick, we can build a polynomial that crosses the x-axis that many times. Is everybody okay with that? Okay. So let's talk here about a way to find some of these points, and we're just going to use our calculator to do that. So let's say we want to find the extrema, and we'll also find the x and y intercepts for the polynomial function x cubed minus x. Let's do that so I can see this all at the same time. All right. So I went to the y equals menu and I just typed in x cubed minus x. Now, to graph this, what I'm going to do is I'm going to pick the zoom, or I'm going to press the zoom button and pick the standard option, because I know in the last chapter we've been graphing scatter plots and my window is probably all jacked up into something like cuckoo crazy. And the zoom standard is a nice way to just return my window back to something that's kind of sensible for just graphing a regular old polynomial or whatever. Everybody's okay with that? Just like the zoom stat was a nice shortcut if you're graphing a scatter plot just to get something that'll show you the scatter plot nice. The zoom standard is typically going to take you back and give you something that you can at least see what it is that you graphed there. Now, when I look at this, though, I'd like to see a little bit more of what's going on here. It's kind of far away. There's a lot of empty space along the edges. So I'm going to adjust my window now some more. I did the zoom standard just to get like something that I could look at, but it doesn't mean that like I can't get a better picture out of this, which is what I'm going to do. So if I look at, it appears to be like if I go from like -3 to +3 in both directions, that ought to give me a pretty good picture. It doesn't matter so much what those values are. I just want to see a little bit more of what's going on, particularly just to make sure I'm not missing any extrema here. Everybody cool with the picture we got? So in this side of this picture, I'm satisfied with this because I can see all the extrema and I can see all the intercepts. So I feel pretty good about what's going on here. Everybody cool? All right. If I look at the picture here, I see one local maxima, or maximum, right here. Everybody agree? I see one local minimum. I see a y-intercept that is possibly also an x-intercept. It appears it's crossing at 0, 0 there. And I see two other x-intercepts, assuming that this x and y-intercept are the same, which is what it looks like from the picture, right? Okay. So what I'm going to do is I'm going to show you how to use your calculator to obtain all those different points. Cool? All right. So what I'm going to be using is all the operations on my calculator I'm going to be using are going to be done on the graph, and they're all located in the calculate menu. So I'm going to press second and then the trace button to open up the calculate menu. Let's find the local maximum first. To do that, I'm going to choose the maximum command. Now the calculator is going to ask me 3 questions. It's going to ask me for a left bound, a right bound, and a guess. So I just need to start by moving my cursor somewhere to the left of where that maximum appears to be. So over here looks pretty good, definitely on the left side of it. So I'll press enter. And then it asks me for a right bound, so I'll do the same thing. I'll just move my cursor over to the right side, press enter, and then it asks for a guess. As long as I only have one extrema in between my left and right bound, which is the way I'm going to choose things, your guess doesn't really matter, so I'm just going to press enter again rather than wasting my time pushing buttons. And it spits out that that maximum is at -0.577, comma 0.385. Everybody cool with that? Okay, let's find that local minimum next. You might have noticed when I entered that calculate menu by pressing second and trace, there was a minimum command there also. That's what I'm going to use to find the local minimum. So again, it's going to ask me the same 3 questions, left bound, right bound, and guess. So I'll just move somewhere left of my minimum, move my cursor somewhere to the right of my minimum, and then press enter for a guess. So there's my local minimum at positive 0.577 and negative 0.385. Everybody's okay there? All right. Let's find the y-intercept next. So to do that, I'll press second and trace. This time I'll choose the value command. So the value command is asking me to give the calculator an x coordinate, and it'll find the y coordinate point, or the y coordinate that goes along with it. What is the x coordinate for every y-intercept? 0. So when I'm looking for a y-intercept, I'm always going to pick 0 for x. And then I just press enter and it says, oh yeah, the y coordinate there is also 0. That's not very satisfying, but does support exactly what we saw in the picture. Everybody's cool? Okay. Next, we'll find the x-intercepts. As an aside, x-intercepts are oftentimes referred to as zeros, and it's because the x-intercepts always have a y-coordinate of 0. That is, that it's basically you're solving where the function is equal to 0. That's why we sometimes refer to them as zeros. And that's the notation that your calculator is using. So if I press second and trace, I look at the second option, there's the 0 command. So that's what I'm going to use to find those x-intercepts, or zeros, for the function. We use those two terms interchangeably. And it's set up the same way. I'm going to have to find them one at a time, but it's left-bound, right-bound guess. So I'm going to find this one furthest to the left to start with. So that's left of the x-intercept. I'll press enter, move to the right, press enter, and then guess. I just press enter. So that's -1, 0. I know that this one is also an x-intercept because the y-coordinate is 0. So I don't have to bother with actually using the 0 command to find that one. I kind of got a twofer. Will that always be the case? No, typically your y-intercept is not also an x-intercept. That only happens when you're crossing through the origin. And then let's just find that last one. So again, left bound, right bound, guess is at 1, 0. Again, that's what it looked like from the picture. So just as a summary, that calculate menu you get by pressing second and then trace. We used the maximum command to get the all your maxes. We use the minimum command to get the minimums. We use value with x equals 0 to get the y-intercept. And we use the 0 command to get the x-intercepts. And all of that is under the calculate menu by pressing second and trace. Is everybody cool? Using your calculator to do this. Again, we did this in your Algebra 2 class, but forgetting how to use the calculator, functions that we don't use all the time, is pretty easy to do. So that's the point of kind of just running through things again. Everybody happy so far? No big deal yet. Just some definitions and using the calculator a little bit. This is pretty nice so far. An important theorem that's going to be very useful to us here. The majority of what we'll end up doing this chapter is going to be like solving polynomial equations. And if we know that the x-intercepts are all going to be solutions to our polynomial equation, so knowing the number of zeros is going to be really helpful to us because they give you an idea of how many solutions our equation can have. So this theorem here is actually a corollary to the fundamental theorem of algebra. The fundamental theorem of algebra just states that all polynomial equations are solvable. That's pretty exciting. It doesn't tell us how to solve them. But it does tell us that a solution can be found. This corollary gives us a little bit more indication. It says that a polynomial of degree n will have at most n zeros and at most n minus 1 extrema. So key here is at most. So does that mean it'll have exactly that many? It could, but it could also have less, right? So for example here, say that we have this polynomial. What's the degree for this polynomial? It's 4. Remember that the degree is just the biggest exponent on our variable. Since this is 4, how many zeros can we have? You could have 4, 3, 2, 1, or 0. We don't know for sure, but we know it can't be more than 4. And how many extrema can we have? Three, 2, 1, or 0 extrema. Again, because we have n minus 1 extrema. So 4 minus 1 is just 3. Is everybody okay with that? Now we could tell if we graph this thing how many we have there, but the point or the hope here is that moving forward we'll be able to do some of these things that we just did with the calculator without a calculator. Be able to do this by hand numerically. Okay with that? So far so good? Okay. So we'll revisit that theorem a little bit later when we start actually getting into solving things, because it's an important tool for us. But for now, we're just going to kind of let that sit. The last thing that we want to do today is talk about end behaviors. And remember, the end behavior describes what the arrows on a graph are doing. And we talked about end behaviors last year in your Algebra 2 class. You might remember the phrase or even remember how to do it. We're going to extend this idea a little bit here and get a little bit more technical in the way that we're describing an end behavior. So we're going to be using something called a limit notation. So the way we're going to write that is we're going to write the letters LIM, and I usually write it cursive when I do that because the letter L looks a lot like a 1 and I don't want it to turn into like numbers and variables here. I want it to look like a word. Underneath this, we're going to write an x with an arrow, and then we'll fill in something for the x here in a moment. And then we'll have the name of our function. Let's just say our function is f of x. And then it'll equal something, and we'll fill that in just a moment. But this is basically what limit notation looks like, where there's two things we need to kind of fill in here. Yes. Sure. Is everybody okay with that, at least as a framework? So every limit or every end behavior that we write is going to be something that looks like this. The only thing that's going to be different is the function that we're filling in for f of x, and then whatever we're filling into the yellow spot and the blue spot, depending on the graph. Or some other analysis that we might do. Is that okay? All right, so I'm going to just draw a little picture here, and we'll do some, write some of these limit notation end behaviors just for some practice to get used to this notation and kind of revisit what an end behavior is kind of saying or doing. Okay with that plan? So let's see. I'm going to put a couple asymptotes in here to make it complicated enough that we can get a lot of practice out of one example. Let's see. Okay. So here's my function. I guess we'll give this function a name, right? It's called f of x. So how many arrows do we see on this graph? 6. So this graph has 6 end behaviors. Yuckarooski, Mr. Kulik. Well, you won't have to do an example this complicated, but I just wanted to give it something that a lot of end behaviors on it, so we get a lot of practice using this new limit notation. Okay with that? So we'll start by kind of writing the framework here, and starting with our first limit, our first end behavior. So I'm going to be filling in here what's happening to the x-coordinate at that arrow. And filling in blue, we're going to write what's happening to the y-coordinate at that arrow. So if I look at the arrow that I've labeled with the number 1 that I've circled in yellow, that arrow is pointing straight to the left. Everybody agree with that? Notice that there's a horizontal asymptote on top of it that we can assume is kind of bounding that arrow from above, that it's not going to jump over that asymptote. Everybody kind of agree with that? So that arrow, the x-coordinate, moving to the left is getting smaller and smaller and smaller and smaller. So what value is that? What value of x is that approaching then? Negative infinity, right? Because it can keep going left forever. Everybody's okay with that? So we'll write a negative infinity down there in the subscript. Now, what y-coordinate is that arrow approaching as it's moving to the left? Well, it's not going up forever like this. It's stuck underneath the horizontal asymptote, right? So the y-coordinate it's going to be getting closer and closer and closer to is just 1. Is that okay? We got a bunch more examples, so if it's like, I think I got it, but I don't quite got it, we'll have a lot of chances to do this. So hopefully by the time we're done, we're going to feel like, oh yeah, I think I got it. So next one. Looking at the second arrow, the arrow that I've circled in yellow and labeled number 2. What x-coordinate is that arrow kind of heading towards? Notice that arrow's basically going straight down, right? So it's stuck heading to -3, which is the value of that vertical asymptote that it's butted up against. Does that feel okay? And because it's pointing straight down, what y-coordinate is it heading to? -infinity. Let's look at the third arrow there. What is that x-coordinate heading to? Still butted up against the same asymptote, right? So it's still heading towards the same x-coordinate as the previous one, which was -3. Does that feel okay with everybody? If it's not, please speak up. And since that arrow is pointing straight up, the y-coordinate is heading to +infinity. Let's look at the one we've labeled as 4 that I've circled in yellow. What's going on here? What x-coordinate are we heading towards? 2, and the y-coordinate? -infinity. Is everybody doing okay with this? Is this feeling like it's getting a little bit clearer? This is why I just wanted to do something with like a bunch of examples, because, you know, you got a bunch of things that could kind of happen, but we'll kind of cover them all inside of one problem. You know what I mean? All right. 5. What's going on here? 2 and x is going to 2, y is going to -infinity again. Yep, that's right. And then the last one is 6. What's this one doing? X is going to +infinity, and the y is going to +infinity. There's no asymptotes getting in the way of that thing. It's just going to continue going to the right and up forever. Everybody feel okay doing this and using the notation? Here's the nice part. For polynomials, How many end behaviors can you have? Exactly 2. You're never going to have any asymptotes for a polynomial. So it's just either going to be going left and down or left and up, or right and up or right and down. Those are like the 4 different possible end behaviors you can have. And you're always going to have one of the ones going to the left and one of them going to the right. Okay, so this one, when we did the end behaviors here, we looked at the graph and used our eyes, right? What if we had asked you to do this numerically instead of graphically? So because this is a polynomial function, I know that it's connected all the way in between. So I'm going to have one arrow pointing to the left and one arrow pointing to the right automatically. I know that because this is a polynomial. Is everybody okay with that? The polynomial has no asymptotes or breaks, so the only things I have to worry about are the very far ends of my graph. One is always going to be pointing to negative infinity. One's always going to be pointing towards positive infinity. I just have to decide what the y-coordinate is doing there. Does that make sense to everybody? All right. The way I'm going to do this is I'm going to just make a little xy table and kind of test my y-coordinates. So I'm going to see what happens as they get smaller and smaller and smaller. So I don't know, I'm going to pick negative 100, negative 1,000, negative 10,000. That seems like I can get a pretty good idea of what's going on, whether that's heading up or down. And over here, going towards positive infinity, I'm just going to pick jeepers creepers. The same thing, but with positives. Now, do I have to use these same 3 numbers, Mr. Kulik? No, I mean, you could do like 56 and then like 529 and like 17,432. You know, it doesn't really matter the numbers you're picking. They should be getting progressively larger, and they should be getting a lot larger. Like these are a factor of 10 each time, but like there's nothing magic about these numbers. These are the numbers I would encourage you to use, though, because they're really easy to type in. Okay, so what I'm going to do then is I'm just going to type negative 100 into the calculator, and then negative 1,000, just kind of see what the y-coordinate is. But I don't want to have to type this in over and over and over and over again, because that stinks. So what I'm going to do is I'm going to type my function f of x into my y equals menu. And then from the home screen, I'm going to go and retrieve the y1, just like we did when we made predictions in the last chapter. So I'm going to press the vars button. I'm going to go over to y-vars. I'm going to go to function. I'm going to pick y1. And I'll do like y1 of negative 100. So there's my value. I didn't have to plug that negative 100 in or type it in for any of the stuff. I just let the calculator do it. And here's the best part. So if I press second and enter, I can just go back and edit what I just typed in. So I don't even have to search through all those menus to get the y1 to come back. So let's see, what do I got here? I got, oops. Give that back again. So I got negative 2 million and some change there. Then I got negative 2 billion and some change there. Oops. 2 nines. And then I got ten to the 12th. What is that? That's like 12 zeros. So that's thousands, millions, billions, negative 2 trillion, I think, is what that comes out to be. Woof! What's going on here? Where are we heading towards? Negative infinity, right? That's getting super negative. Very, 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 very small. And I'm just going to do the same thing with the positive values. So again, I'm just going to press second and enter to pull the y1 back and just delete out the negative and a couple of zeros. And I got just shy of 2 million. Just shy of 2 billion. And then just shy of 2 trillion. So again, what does that all mean to me? To positive infinity. So if we ask you to like support your answer with a table, this is what we're talking about doing. And I would encourage you again to use your calculator and let the calculator do all the heavy lifting for you. Type the function into the y equals menu and use the y1 command so you don't like goof up a parenthesis or like mistype a number. You have to do that over and over and over again. It gets pretty, if the polynomial is long, it gets super annoying to do that. This is very nice and easy to just have the calculator plug the number in for you. You know what I mean, guys? So take advantage of your calculator to do the tedious parts for you. This is where we're going to stop today. So at this point, you guys should be able to do up through 8. On the homework set. Remember, next time on Thursday is going to be the test day. If you haven't turned in a half sheet of your notes, you're entitled to do that if you'd like. If you get them to me sometime today or before school tomorrow at the absolute latest, that's okay. But after first period tomorrow, I'm not taking them. Okay? So if you want to give it to me now, today, I'm happy to take it. If you want to wait and it's like I still need to do that, that's fine, no big deal. You come back and get it to me later. But tomorrow morning is the absolute latest. You can get it to me, must be to me before first period.
I got a question.
Sure.
I was just looking through it. Could not figure out what the first question of the test formula